Nice. Okay.
Okay, let's start it.
Yeah, let me start the record.
Okay. Okay. Hello, everyone. So good morning. My talk is about fundamentals of quantum computing and quantum tensor networks. I'm Jun from Georgia Tech. So in this talk, we'll just introduce the fundamentals of quantum computing. Then we show how to about something about the quantum mechanics, about the linear algebra. Then we'll show you as a quantum universal case. After that, I will present some our recent open work, research work about introduction to quantum tensor networks. We just show the tensor decompositions, and then we'll give you an introduction about the quantum singular value decomposition. Okay, the first part is about the quantum computer. Okay, so what's the difference between the classical computer and the quantum computer? Quantum computer considers the two most important characteristics. The first one is about the superposition. Superposition means that for n qubit, for classical qubit, there's only one pass at one time. But if you consider n qubits, it's about totally about 2 to the n pass at one time. So just one quantum state just correspond to all the linear combinations of all the 2 to the n pass at one time. So this property, we call it is a superposition. The second characteristic for the quantum computer is entanglement. Entanglement means if there is two quantums get connected or get entanglement, there's either change of one state, maybe it's directly affects the other one. Okay, so this property we call the quantum entanglement. Another one is important issue is about the quantum computing timeline. For the classical classical computing, it spans about more than 100 years before it get matured. Currently, that we have a very powerful GPU in 2017 contains 19 billion transistors, but it's from the beginning just get started from the quantum vacuum tube in 1906, and in the mid of the 20th century, we developed integrated circuit. And now we have a very super powerful GPUs used every day, especially for some deep learning architectures and deep learning applications. The GPU plays an essential role in those applications. But the quantum computing goes quite different way. It just gets started in 1980s. At that time, some guys want to propose a quantum simulator. They want to simulate the quantum mechanics. That's in the late days of 20th century. This D-Wave just developed the first generation about quantum annealing quantum computers to approximate the quantum optimization algorithms. And the Shaw's algorithm was very famous at that time. It became very famous to decrypt any RSA protocols if you have very super powerful quantum computers. Until recent days, maybe there's a few qubit quantum processors. About 2 years ago, Google announced their quantum advantage because they developed their 53 qubit quantum computers. They announced their quantum advantage because you have a stable 50 qubits, so many applications can be used in quantum computers. So just IBM just shows a timeline for the development of quantum computers. Currently, we just notice in the 2021. Now, this year, IBM just announced their 127 qubit quantum computers. And if I have such a quantum computer, it allows so many applications for finance, for machine learning. and then for the some natural sciences, and we can do some combinatorial optimization. So if the traditional problems be hard, but you can formulate it as a quantum computing format. So we can make advantage of quantum computers to speed up such a combinatorial optimization problems. But in the next few days, maybe it's 2 or 3 years. In the next few years, maybe it's we need more powerful quantum computers, because IBM can develop more than 1,000 number qubits, and at that time maybe it's more natural sciences fields and combinatorial optimizations can be widely used in practice. For example, some hedge fund companies, we can use a quantum computer to heighten their eyesight. We can use quantum computing to enable large data machine learning applications. So it's that within the next few years we can see this progress. So it's a high time now we just practice with our muscles in the quantum computing. IBM just used the superconducting is a technology to develop their quantum computer. But for the Anq just a startup, very famous startup in the US. They're based on there is a trap-down technology. They have a different roadmap for the growth of market leadership in the quantum computers. They currently have 22 qubits nowadays, but in the next several years, maybe they enable 35 qubits, and at that time machine learning application can be placed on their Anq quantum computers. And in the 2028, we can hopefully they can use their quantum computer to support quantum chemistry and do some combinatorial optimization applications, because at that time they have stable more than 1,000 logic qubits at that time. Okay, these are the 2 roadmaps for IBM. IBM based on the superconducting technology, and there is another roadmap for Anq. Anq is based on the trap-down technology. So these are 3 basic problems for the quantum computing. It says 3 quantum computing problems. The first application one is for the application of quantum finance. Quantum finance means that there are so many important issues in this field. For example, the RSA key decryption. For the classical computers, if the bit length of RSA key is quite long, it's impossible to decrypt such a RSA protocol, because it takes the age of universe time to get the private key. But for a quantum computer, it's quite different. It's even for the key length is about 2,000. It takes about 1 hour to get the private key. So it's insecure for if I have a powerful quantum computers. So, but for the classical computer, it's a quite secure algorithm. But for the quantum computer, it's not the case. So this is how to anti the attack of the quantum from the quantum computers in power issue and central issue in the cybersecurity, for the RSA protection, for the cryptocurrency. So there are so many issues with the quantum finance. But the full application of the quantum chemistry, quantum biology, because of the quantum algorithms can allow us about quadratic speed up for the combinatorial optimization. So there's so many applications can be feasible. So many NP-hard problem can be feasible in near future if quantum computers come to exist. Okay, so these are very interesting topics about interesting topics about quantum computing for the finance, for the quantum biology, quantum chemistry, and the quantum optimization problems. So this the basic introduction to quantum computing, and it is the outlook of the future work in this field. Well, next we just go to our topic about fundamentals of quantum computing. Firstly, I'll just show you the quantum mechanics, linear algebra. Then I will show the quantum universal case. After this session, I will show you the introduction to the quantum tensor networks. So this is a basic introduction to quantum superposition. For a simple quantum system, a single quantum bit can be described by the Dirac notation. Dirac notation means that it can be seen as the vector for a single quantum bit, if it corresponds to the two-dimensional vector, and in each element corresponds to alpha, and the first element corresponds to alpha, the second one is related to the beta, and there is a Born's rule. Born's rule means that the sum and the square of elements equal to 1. And then we'll see that is the Chi-psi. Chi-psi means that is the quantum state is located in the two-dimensional Hilbert space. Another thing that was a qubit is a single qubit can be represented by the two basic Chi's. The first basic Chi is a Chi0, and the second one is a Chi1. And the Chi0 is correspond to the 1,0 element and the vector in the Hilbert space, and the Chi1 correspond to the 0,1 in a two-dimensional vector in Hilbert space. And for every qubit psi is a superposition of a Chi0 and the Chi1 states. So the Chi-psi Chi-psi is just a linear combinations of Chi0 and the Chi1. Okay, this is the basic the definition of quantum superposition. The second the definition about quantum entanglement. Quantum entanglement means that for two qubit, imagine that we have two qubit state in a tensor product of the two Hilbert space. And this is for such a two qubit state can be decomposed a linear combination of the spanning of the basics in the tensor product of the Hilbert space, but they cannot be decomposed into the direct tensor product of two Chi's in the Hilbert space. So also it can be seen as a linear combination, but it cannot be directly decomposed into a tensor product of two vectors. So if such a case holds, we can see that this property as the quantum entanglement. So quantum entanglement is quite important. It means that it corresponds to so many important properties. So in quantum communication, in quantum sending. So that means another property is that any quantum states can be written in the product form. So if you have such a characteristic can be held because these are two quantum states get entangled. Otherwise, they are unentangled. So the entanglement is quite important because it enables the scale of parallelism in the quantum computing in practice. So after these are two basic characteristics, another thing is that how to measure a qubit. Quantum states are now directly accessible. It's now quite different from the classical computers. Classical computer, if you get some result, you can directly get access to the result. But for the quantum computers, quantum states are now directly accessible. You have to do the measurement after you obtaining the result. So this quantum results must be measured. So if I have to measure the quantum state psi, a quantum psi consists of the basic state Chi0 and another basic quantum basis Chi1. At one time, you have to observe only one basic state, maybe it's either is a K0 or is a K1. And if you observe the K0, it has a probability of the alpha square. But if you have to observation of K1, it corresponds to the probability of beta square. So this the uncertainty property for quantum measurement. So if you want to measure the qubit again, you often can J with certainty. So in other words, the qubit has collapsed to a classical state. The superposition has to be destroyed. So after measurement, there's no superposition, and this superposition quantum superposition property existed. So this measurement can destroy this property. So how to do the measurement is an important issue. You have to, maybe it's you want to make the entanglement time longer. You have to measure the qubit in the mid of quantum computing is to maintain longer entanglement time. Maybe it's otherwise you have to measure the qubit in the end. Maybe it's, you have to ensure this stable entanglement time during the communication of the qubit. So this is a very important issue, how to do the quantum sensing and the quantum measurement. Okay, the second important issue is about quantum universal gates. So there's a comparison between the universal classical and the universal quantum gates. For the classical universal gates, there's about 7 universal gates. Is AND gate, OR gate, NOR gate, NOR gate. So there's so many as 7 totally different classical universal gates. If you use these basic gates, you can set up any kinds of target function. That's why we call it universal, because any target function, maybe smooth and non-smooth, continuous functions, goes back to the combination of the 7 basic classical gates for a classical computer. But similarly, if we consider quantum gates, it allows more than 15 universal gates. So maybe and each universal gates can be all the quantum universal gates can be used to set up very complicated target function. And maybe it's because for each universal quantum gates, it has a more representative, because each universal quantum gate corresponds to a matrix. So it has a more powerful representation powers than classical universal gates. I mean, it means that you may use much fewer quantum gate, universal quantum gates to realize many complicated target function. So this is the demonstration of the basic the universal quantum gates. For example, this is identity gate. Identity gates it corresponds to the matrix representation, identity matrix. Another one is IJCAI gate. IJCAI gate is to allow the qubit to rotate along the axis. And another one is Y gate. Y gate means it's rotate along the y-axis. So means more important is the gate is a signal gate. Signal gate means that is a target qubit as a control qubit. If the target qubit, maybe the states can be changed according to the control qubit. So this another thing is that the signal gate is a 2 qubit gate. It's with an important. If you have a 2 qubit gate based on the signal gate, maybe we can select some 3 or 4 basic 1 qubit gate. We can just build up as a universal set. And only we use 5 or 6 basic 2 qubit gate and 1 qubit gate. We can realize any complicated target functions. So this is the basic concepts of the universal quantum gates. Another important universal quantum gate is rotation gates. Rotation gates means that it has some free parameters. Free parameter means that we can adjust the angles of the rotation angles of qubit. So this if want to do some quantum encoding, we want to do some quantum machine learning. The free parameters is associated with the rotation angles. So this rotation gate is quite important for the applications of quantum encoding and quantum machine learning. So in the Yanqi just mentioned that if want to do some backpropagation to fine-tune the free parameters, in fact, you just fine-tune the rotation angles of quantum qubit. So this rotation gate is quite important. It just it can be important to how to get the exact angles in machine learning and for some coding work. That issue is quite important. So this basically we have some deterministic gates for the universal quantum gates that are deterministic. Also, we have some parametric gates. Parametric gates is correspond to some universal rotation quantum gates. We can always use such a rotation quantum gates as the operator to change the state of qubit from one state to another state. Also, we can use such rotation quantum gates to compose the variational quantum circuits. Here is the example shows that we use the rotation gates to set up the unitary evolution of a density operator. Is for a quantum circuit, which consists of combinations of universal quantum gates. For each quantum gate, it corresponds to a unitary operation on qubit state. So for at the very beginning, there is the chi psi. After we use this quantum operator, you can change to this u multiplying chi psi. You change to another quantum state. But for such a quantum operator, is always a unitary operator. Unitary operator means that the inner product of the matrix is equal to the identity matrix. So that's quite important because for setup for any the variation quantum circuit is always a unitary operator. It's always a linear one instead of the nonlinear one. So for quantum neural network, for the quantum machine learning applications, if you want to use the quantum transformation from one state to another state based on the quantum operator, so this is always a linear operator instead of a nonlinear one. So this the representation power should be studied, because if only consider the linear operation from one state to another state, so this is another issue that quite important. It's called, if we have a gate set lambda as if we see that a set is universal, so for all the general surface C, the following statements always hold. That means that for any approximation error, we always can somehow to choose some universal quantum gates from the side, so that for any target quantum gate, we use the basic universal quantum gate to approximate such as the target gate. So this is a property, and we call it. It is a universal approximation by using the universal gate quantum gates. But if we consider this the variational quantum gate, we can somehow to fine-tune the parameters to approximate any target gate. So for if we don't use the parametric quantum gate, somehow we can set up there are so many deterministic quantum gates to approximate any target gate. Eventually, we can find we can best approximate such a target gate, but you have the parametric quantum gate, we can fine-tune the parameters of the free parameters of the rotation gate. And finally, we can approximate the target gate when the free parameters of get converged. So this is important. If we can make use of rotation gates and based on the machine learning optimization algorithms to approximate any target gate, instead of use so many quantum universal gates to approximate a target gate. So this is the important characteristic on universal gates and to approximate any target gate. Okay, this is a basic introduction to fundamentals of quantum computing. The first important issue is based on the linear algebra here in the field of quantum mechanics. The second important issue is allows universal quantum gates to approximate any target gate. It's quite similar to the classical approximation algorithm, but here we just use quantum universal gates. Just the last issue we want to talk about is quantum tensor networks. It covers two basic topics. The first one is the tensor decompositions. The second one is still an open question: how to use the quantum singular value decomposition to realize some tensor quantum tensor decomposition properties. So this picture shows a basic understanding about the tensor decomposition models. For example, there is a traditional Tucker decomposition. Tucker decomposition means that you want to decompose a multidimensional tensor into the summation of the multiplication of the matrix. And this is commonly used for the high dimensional vector decomposed to smaller factors. Another tensor decomposition commonly used today is based on the tensor twin decomposition. Tensor twin decomposition is quite different. The basic idea is to decompose a multidimensional tensor into the 3 or 4 order tensor, small co-tensors. And they both Tucker decomposition and tensor twin decompositions are based on the SVD variance. For the Tucker decomposition is based on high order SVD, and tensor twin decomposition is based on tensor twin decomposition. Tensor twin SVD. Tensor twin SVD means that we want to iteratively to make use of SVD to find the core tensors instead of just decompose all the factors at the same time. So this core issue is how to set up a single value decomposition as a quantum format. Well, recent work shows that we can formulate such a problem as a bipartite system and make use of bipartite pure state for set up quantum singular value decomposition. So what's the bipartite system and states? Is for SVD, we can consider two important transformation matrices. So we have to decompose all the qubits to the two sides. The first side is corresponding to Alice observation. So if Alice subsystem can be described by the first Hilbert space side CA, and Bob's one is related to another Hilbert space CB. The compounded bipartite system can be described by tensor product or two space is a tensor product of two Hilbert spaces. So another definition is about bipartite pure state. If this the tensor product of two Hilbert space can be seen as a whole Hilbert space defined as a tensor product of a two Hilbert space. So in doing so, we can decompose a quantum state as the linear combination of the bases from the two Hilbert spaces. At that time, if we use the traditional SVD, this operation to traditional SVD for this traditional vector in a direct notation can be decomposed in as the linear combination about the orthonormal bases or two orthonormal bases in two different Hilbert spaces. This is quite important definition that convert the classical SVD into a direct notation. After that, we can just try to use the orthonormal transformation to the basic quantum basis for the from the Hilbert space A and another from Hilbert space B. After that, we can realize the mathematical expression of the quantum SVD. But how to design such a quantum SVD in the quantum circuit? So this the basic idea is shown in the picture here. We can set up the variation quantum circuit. In other words, we can set up the parametric quantum circuit to divide the whole qubits as a two observation, two subsystems. For each subsystem, we can use two different variation quantum circuits to transform the inputs into the outputs. So there's in more detail, if we consider for each subsystem, there's 4 channels. We can use so many rotation gates to set up parametric variation quantum circuit. So this you consider only one layer is shown in the picture here. So in doing so, we can just realize quantum SVD. And another important issue is that currently we can realize quantum SVD for the basic idea from the basic decomposition. How to realize very complicated tensor decomposition, for example, for the Tucker decomposition. Another one is for how to realize the quantum tensor train decomposition. We have to just change our quantum SVD to higher order supported, or just need to allow the iteratively tensor train SVD. So this is our current work, how to do such work to realize different kinds of SVD for the tensor decompositions. Okay, these are basic architectures of the quantum SVD, and we think it's important on how issues, because SVD currently used widely used in machine learning and signal processing. But if we have the quantum SVD, so we can allow more, we can place the SVD-based models on quantum computer. So that's one important issues nowadays. Okay, that's all my talk today. Thank you for your attention. Any question, please let me know. Hello, hi. I'll just finish my presentation.